Hello, and welcome to my second presentation in this course. So my name is Rasmus Magnusson, and I have previously given you a short introduction to neural networks, what they are, and when you can use them, and why you would like to use them. And today we will be looking at a slightly more applied and more clearer example of a very specific type of neural networks, namely autoencoders. So let me just share the screen here. There, great. Oops. So autoencoders. So autoencoders are, as I said, a very specific kind of neural networks. But to fully understand what they are and how to use them, I think it's easier to start with a much more simple approach that is very often used when studying data and trying to analyze what data is telling you. We're going to start just by imagining a very simple case where we have observed lots of data of something, and it doesn't really matter what. So we can just imagine that we have 200 observations of two variables. It could be a very common example is petals of iris, so the flower irises. I plotted this example data here on the right, where you have a variable x1 and x2. And just by looking at it, you can immediately see that there is a very clear dependence between these two variables. So it's not really that they are not independent. So if you know x1, you could easily predict x2 and vice versa. That in mathematically speaking, you could say that they are not orthogonal. And as I said, they carry some kind of mutual information about each other. So now imagine then that we, instead of having x1 and x2, we introduce a completely new variable, xi. So I'm using the Greek letter xi here. Where's the pointer here? So xi1. And instead of having the coordinate system where you have x1 and x2, we just have xi1 here going along the mean vector of variance here in this data set. So when you represent your data in that kind of way, it kind of becomes obvious that you don't really need two variables to explain your data. You just need one to at least get most of the variance that you have in data, that is xi. Of course, you can also introduce this xi2 that spans the other direction in this coordinate system. But that is not as interesting because most of the data is distributed along this vector xi1. So this is actually called a principal component analysis. And it's a really, really common tool, one of the most important tools, I would say, in data analysis. However, something that you can see here is that xi1 and xi2, they are linear. So they're actually just vectors spanning along the vector room that x1 and x2 spans up. But imagine then if you have nonlinear dependency between x1 and x2, then doing a principal component analysis becomes really, really hard. Principal components, it's very fast usually, it's very easy to apply. But as I said, nonlinear, you can't really do this because the linear vector won't fit the data with the axis of variance very well. So it would be much better if we could just analyze and represent data in some kind of more a way that is capable of handling more non-linearities in data. And if you watched my other video on neural networks, you might remember that that is really one of the most important things when it comes to properties of neural networks that they can handle nonlinear data. So this is just remember the perceptron and how you would stack them to get nonlinearities when you have a model that can go from input to a specific output that you train it to fit. Well, there's nothing stopping you to do that on a neural network where you have input data and output data to do a nonlinear fit. And what do I mean when I say that? I'll try to show you here. So again, now instead of 2 variables, we have a slightly bigger toy model here of 4 input variables. We have matrix X, which is equal to vectors x1 to x4. These are all different variables. So if it's a person, it could be height, weight, I don't know, eye color and hair color. And you can feed that into this neural network one person at a time with these different traits. And then you can compress down those traits into a smaller set of traits in this latent space that is the neural network that is in the autoencoder. So the autoencoder is a kind of neural network. So sorry for mixing the terms here. So yeah, we compress this vector of 4 values down to down to 3 values, psi 1, 2, and 3. And then you can decompress that back to the full vector that you had from the beginning, but now you've actually lost and recreated 1 variable in the middle there. Maybe we can assume that the color of your eyes is quite correlated to the color of your hair if this was on the input layer. So maybe you don't really need to represent those 2 things as 2 individual variables here on the input and output layer. So they would basically be stored on the same neuron in the middle there of the latent space. And you can just train this model to learn how to compress this data by minimizing the square difference between the input and the output data. Okay, so this is really good because it makes us to be able to both represent data in a very handy and compact way, but also that the things that the autoencoder learns in the latent space becomes quite important or quite efficient way to find hidden structures in your data. So actually you can go if you have lots of input variables, but very few of them are important, and that is that most of your variables correlate a lot. Then you can actually get that down to just a single variable that holds information of all the correlating ones, because they're basically the same, all of them, just as the hair and eye color was the same in the previous slide. And as I said, then studying what structures these models learn in the latent space, you can find very complex patterns that are not really obvious to a human trying to get a hold on or trying to get a feel of what the data is telling me. So that was a very short introduction to what neural networks and specifically what autoencoders do, and we will move on to giving some examples of where we have used autoencoders in real life. So something I've been working a lot with is gene expression data. Since you have mRNA of every gene floating around in the cell, how much you have of each gene tells you something about the status of the cell. So of all our about 22,000 genes, 22,000 gene expression variables, that's quite a lot of data that's very hard to interpret. Something we would like, and also the dependencies between genes are very nonlinear. So trying to understand exactly what is going on in the cell using an autoencoder is something that is very important, or using an autoencoder is a very important tool to try to understand that. And when you do that on gene expression data, what you see is that the more you compress the data, that is, the fewer the variables you have in the latent space to represent a gene transcriptomic profile, the more general representations you have in the latent space. So if you have quite a lot of these variables, quite a lot of neurons here in the latent space, then maybe you would see that each neuron represents not too complex things, maybe pathways, that all genes that are related to one pathway would become encoded in a single variable here. And if you have very few of them, maybe you get even bigger, multiple pathways that overlap become encoded to the same things. So it's a way of creating or teaching the autoencoder complex patterns, to find complex patterns of big sources of data. Also, something that a lot of people have used, especially in the beginning of when researching autoencoders really took off, was to impute missing values in data. So if you have an autoencoder here that has been trained and it knows basically to take in data and recreate it again on the output here, then maybe you can come with a new data set here that is missing a value. So you don't have a value for X3, which is very common also when you look at especially single cell transcriptomics data. If you feed that into the model, you get the latent space representation here, where, remember, each model or each value here for each hidden variable is a sum of a nonlinear dependency of the inputs from x1 to x4, and you decompress this representation, you will actually have estimated x hat 3 here based on x1, 2, and 4. So we will actually have something that a good approximation of what x3 should have been if you would have observed it in the data from the beginning. So that is a very, very important tool to find missing values. If the autoencoder maybe had been trained to look at images and you have something that's very blurry, the autoencoder would have also filtered away the noise, so you don't really have representation. It doesn't know noise, so it would just know the hidden structures that could be in the images that the autoencoder had learned. So that's also something that's very important, a very important use when it comes to autoencoders. And as I said, the structures that become embedded in autoencoders can be very complex and very interesting when it comes to analyzing big amounts of data, large amounts of data that have very unclear structures hidden in them. So here we can just assume again 4 variables that we feed in of some kind of data in this toy model that are compressed to three latent space variables, xi1 to xi3. If you have trained the model to do this many times, maybe you're interested in actually what's going on here in the latent space, then you can take these values here for each node in latent space, and you make a small change. Maybe you add a small floating number to one of the variables here. I call eta this addition, and just basically you perturb the latent space and observe what happens then on the output when you recreate these the changes, and then you can compare this delta x1, that is the change between the x hat and x from the beginning here, and x2 is the change from x2 hat to x between x2 hat and x2. And you can see if this variable has changed a lot here because of this eta, you know that x2, which would be this node, I guess, that it change these that x2 has really something to do with this hidden node here. So it's a way of extracting patterns that are quite hard to get from the latent space. And there is really a lot of ongoing research here. So now it's quite close to what is cutting edge science, I would say, how to take these very complicated hidden structures that you get in these complicated and convoluted models. And I mean convoluted in the sense of complicated, and extract those hidden structures, because that has not really been obvious so far. And the last thing I'm going to show you is variational autoencoders. So here things get a little bit complicated, but if you feel that my very short description of it is not enough, I really, again, strongly suggest that you seek out the YouTuber I mentioned in my previous video, Blue Von Braun, is it? I don't remember. But there are also just, if you just Google or search YouTube for variational autoencoders, you will also get very good descriptions. In summary, a variational autoencoder is just an ordinary autoencoder, but instead of having one value per variable in the latent space, in the hidden layer, you actually have two values. So instead of having one value, you have a distribution. You have a mean value, a mu, and you have a standard deviation from that mu, such that each time you pass data from the input layer to the output layer, you actually get a random sampling from this distribution. And that is a very, very important development that has enabled a lot of research into actually being more easily being able to extract these hidden structures that we have in data. Because if you have a distribution here, these perturbations, the eta addition that we saw in the previous slide, will actually you will be certain that you're still on some kind of distribution. While if you don't have this specific requirement of having a distribution in the latent space, 2 points in the latent space that are very close could still be very different on the output layer. So it's not really certain that the decompression has something to do with the input. So I think in the lab you will be seeing a little bit of variational autoencoders and then playing around with them, which you will have on Thursday, I think.